Okay. Hello. Over last weekend, you did some work on this handout, which I called Foerster Conics Packet, which is just a whole bunch of problems. And number one had 6 parts. It was all about degenerate conics. We went over that in class, in all 3 classes. So I'll pick it up from number 2. I really don't think it's necessary that I do all of these, and so maybe I won't. I don't know, but number 2 might be helpful to some people to see this being done. So I guess I'll just very quickly do these 4 problems. 4x squared minus 25y squared equals 100. B is x squared plus y squared equals 49. C is x equals negative 1/3 y squared, and D is 24x squared plus 4y squared equals 96. Okay, so these are all, I think, straightforward problems. Yeah, we need to understand conic sections, and we need to understand these second degree equations, which turn out to be conics. So let's go. In each case, I'm going to convert them into a kind of a standard form, and then use my knowledge to make a quick graph. I think that's the only directions, right? Yeah. So rough sketch, I said even. Okay, divide by 100. We get x squared over 25 minus y squared over 4 equals 1. And yeah, before break even, we learned that means we are going to have a hyperbola centered at the origin, stretched out by 5. So this is now even more than a rough sketch. This is like a good sketch. And yeah, there's my happy box. It's being stretched out by a factor of 5 in the x direction and 2 in the y direction. It's going to be a horizontal hyperbola. So that's all you had to do. Boom. Okay, good. 1 down, 3 to go. Part B, dude, this is just a circle. So, you know, don't forget about circles. Great. Circle radius 7. What's this? You could actually know almost nothing about parabolas from the geometric perspective, and still have a pretty good idea of what this looks like, because it's going to be a sideways parabola, and the negative means it's going to open left. That's what we knew even before this unit, but you know, our geometric analysis of the parabola based on the definition of the parabola involved the parabola being in the form y squared equals 4qx, and so keeping in mind that is the sort of generic equation for an x equals parabola, or a y squared equals parabola, q telling us how far the vertex is from the focus and how far the vertex is from the directrix, means I kind of do want to get it in this form. So alright, so I'll take my equation and I'll write it as y squared equals negative 3x. And alright, well, if negative 3 is 4q, or personally I always think of q as being positive, then q is 3/4. Okay, so not only is this a parabola with vertex at the origin opening left, that I knew already, but if I wanted some more detailed information about this, I know I said rough sketch, so maybe you didn't even have to do this, but there will be a focus at negative 3/4, and the directrix will be x equals 3/4. In other words, q equals 3/4 tells you how far away those things are. The parabola itself is going to open like this, and I won't try to make it any more accurate than that. Okay, here if I divide 24 times 4, I guess, is 96. So if I divide both sides by 96, I get x squared over 4 plus y squared over 24 equals 1. So this is just going to be an ellipse. And yeah, I mean 24 is almost 25, so this is going to be stretched out by 2 in the x direction and by a tiny bit less than 5 in the y direction. So, I mean, I did say rough sketch, so I feel like that's it. Alright, I now have decided in retrospect that I didn't need to go over these problems at all. I'm sure you agree, but I have done so. So that really did only take 5 minutes. Okay, so with that as our background knowledge, let's do some of the more difficult ones where the equation is perhaps less obvious and some algebraic work is required first. I don't think I want to do all of these. I might just do, you know, like 1 or something, or 2 of them perhaps. I think that's what I'll do. I'll do just like B and C. So I'm moving on to 3 now. 3B says 9x squared minus 4y squared plus 36x plus 8y plus 68 equals 0. Okay, and now we're going to sort of do some tedious work and try to bring some order to this equation so that we can understand it and analyze it. So let's go. I'm going to collect the x terms together. I'm going to collect the y terms together, and I will move the constant over to the other side. Factoring out the leading coefficient and factoring out the negative 4, leaving me with minus 2y. And now I shall complete the square. You can do this on a separate line, but since I'm using colors, I'm pretty sure I'm not going to make a mistake. So I add 4 to complete the square here, but I've really just added 36 to the left-hand side of the equation. So I have to add 36 to the right-hand side of the equation. What's going on here, I need to add 1 in order to complete the square. So I really just subtracted 4 from the left-hand side of the equation. So I need to subtract 4 from the right-hand side of the equation. Actually, this is a nice little problem because some tiny little thing happens which is very easy to deal with, but it does mess some people up. So we get this, and we get this. And what do I have over here on the right-hand side? I don't know. I get 68 minus 32. So whatever that is. 46? That can't be right. Must be 36. Yeah, sorry. Negative 72 and 36 is negative 36, of course. Okay, and so some people have the tendency to sort of like panic here or something. Don't panic. This is negative, so of course I need to divide by negative 36. I mean, perhaps the thing to do is kind of just move everything, right? So like, you know, move this 36 over, move that over. I mean, this is really kind of silly. I'm giving you advice on sort of how to do your Algebra 1, but I have noticed that people will sort of, it's cognitively difficult for people to divide both sides by negative 36 and also like change the order of the two variable expressions at the same time. Anyway, there it is. Indeed, this seems like this is going to be a horizontal hyperbola, but no, because this is negative, when I divide by negative, the signs flip. And so, in fact, it's going to be a vertical hyperbola. All right, what's the equation? Y minus 1. If I now divide by 36 for real, I get y minus 1 squared over 9 minus x plus 2 squared over 4 equals 1. All right, so it's important to get these initial steps right. But here we have nice kind of whole numbers and everything's nice and chill. So what is this going to be? It's going to be a hyperbola. The center is going to be at negative 2, 1. It is going to be a vertical hyperbola, as I said. What else? The y-coordinate is being stretched by a factor of 3, so that means that a is 3. The x-coordinate is being stretched by a factor of 2, so b is 2. C in a hyperbola is always the hypotenuse. And so we get that c is like root 13, which is like, 3 something. I don't know what. And yeah, what else? What were the directions? Maybe I should look at that. For each of the following, yeah, just make a sketch. So actually, you don't have to necessarily, or at least I didn't tell you to, plot all the foci and all those kinds of things, but perhaps I just will anyway, because I'm a math teacher. So here we go. -2, 1 is the center. Boom. The y-coordinate is being stretched out by a factor of 3. So we should expect things to go 1, 2, 3, 1, 2, 3 up. And the x-coordinate is being stretched by a factor of 2. So 2 over. Therefore, the happy box X is going to be here. And the, geez, it looks so terrible, but I guess it's right. And then the diagonals are going to go like this and like that. Okay, and great. It's a vertical hyperbola, we said? Yeah. So A is in fact is 3. So that's another way of putting that maybe is that the vertices are 3 away from the center. Sort of doubting myself, but no, this is good. So what is this point? It's going to be -2, 4, and this point will be -2, -2. They will be 6 apart from each other because, yeah. Okay, good. The hyperbola itself will therefore look like this, and like this, and that's really all there is to say, unless I wanted to say more. One thing more you could say is where the foci are. Where are the foci? They're root 13 away from the center, so going to be like another bit more out over here. Where is that focus? It's going to be at -2, 1 plus root 13, whereas the other one down here will be at -2, 1 minus root 13. And finally, the asymptotes of the hyperbola are going to be lines with slope up 3 over 2. Just look at the happy box and see. But the center is -2, 1, so this is going to be y plus 1, y minus 1 equals 3/2 x plus 2 will be that one, and this one will be y minus 1 equals -3/2 x plus 2. Okay, so I hope that red and green and stuff is visible decently. So, okay, great. That was a little bit of like remedial hyperbola. This is just not, this was sort of, there was almost nothing new in the first part of this homework. This is just practice. This is just pure practice. The only thing different from the work that we did, the only thing different about this from the work that we did from before Christmas break is just that I'm not specifically telling you in advance that it was going to be a hyperbola, but of course you can just glance at it and see that it will be. So, alright, good. Good. Let's get to the new stuff. The new stuff, solving systems of second degree equations. Okay, and yeah. I did things a little bit differently in every class. So let me do, I might just do all of these. So this is now 4A. Let's certainly do 4A, you know, at least. And let's see how long that takes. So 2x squared plus 5y squared equals 98. And 2x squared minus y squared equals 2. Okay, in my opinion, you should use your knowledge of conic sections to produce a sort of accurate graph of the equations first as an aid to solving, and then the algebra stands on its own. I mean, if you do the algebra perfectly correctly, you know, you don't even need to make the pictures, but the pictures I think really help. So Unfortunately, I think these problems were designed so that the numbers work out nicely, the solutions, the algebra that is, but maybe the graphing doesn't. So we just have to be really casual. What do I mean by that? Let's take this first thing. What is it? Well, it's going to be an ellipse. If I divide both sides by 98, I'm going to get x squared over, well, 2x squared over 98 is going to be x squared over 49. So that part's kind of okay. Plus y squared over, and now I get 5y squared over 98, and I think it's kind of worth it to write this as 98 fifths. Alright, but that's a little bit kind of gross, and so you have to just be, not scared of that, right? What is 98 fifths? It's very close to 100 fifths, which is like 20. So if this number is like 20, let's even call it like, 19 point, I guess it just is like 19.8, is that true? Yeah, because it's like 95 and 3/5, so it's like 19.6 even. Then what's relevant to me, and now I'll kind of write this out one more time, is that this is going to be like x, well, maybe I'll even do it like this. You should really think of this as x over 7 squared plus y over, what is the square root of 19.6? I don't know, it's like 4 something. So let's just call it like 4.5. That might be right. 4.4 doesn't really matter, but that's what's important to me. This is going to be an ellipse. And it's going to be a horizontal ellipse, and okay, that's even maybe too much effort. Okay, how about the second one? The second one is going to be some kind of hyperbola. If I divide by 2, then I get x squared minus y squared over 2 equals 1. So that's also perhaps a bit annoying because it means that the y coordinate is being stretched out by a factor of root 2. Nonetheless, I am so good at conic sections that these ugly numbers don't bother me because I'm not trying to be perfect anyway. I'm just trying to get a picture. And so, okay, let's go out to 7 and whatever, and go out to 4.4, and let me graph my first conic. I think this is, yeah, not terrible, but certainly not good at all. And then, what about this other one? Well, this is going to be a hyperbola. What is this hyperbola going to be like? It's going to be centered at the origin, so that's nice. It's going to be horizontal, and well, let's see. The y coordinate is being stretched out by root 2, so and the x coordinate is being stretched out by 1. So I'm imagining a kind of happy box that's just a little taller than it is wide, but sort of like, who cares a little bit about that? It's going to be a horizontal hyperbola centered at the origin, and so the vertices will be here and here, and alright, I didn't time myself, so I don't know how long that took, but I really think that took maybe 3 minutes. What matters is that at the conclusion of this stage of the problem, I can just tell you with a very, very high degree of certainty that this system of equation is going to have 4 solutions. And furthermore, those 4 solutions are going to be completely symmetric. So that's what I should expect. Now, hopefully the algebra, bears that out. Let's go and do the algebra. Well, there's not an exact algorithm for what to do to solve these systems of second degree equations, but maybe that's what makes it kind of more fun or something. You just gotta go with your wits. Here, I think it's very obvious what to do first, and that is, just subtract the 2 equations because it's one variable is then just immediately gone. So if I do that, if I subtract these 2 equations, then I just get 6y squared equals 96. And okay, this problem is just not hard, right? Because that tells me that y squared is 16. That tells me that y is plus or minus 4. And I'm definitely not going to forget the plus or minus 4 because I have this giant picture staring me in the face that indicates that I should expect 4 solutions. So what are those 4 solutions? Well, there are the ones when y is 4. And there are apparently going to be 2 of those this can be seen by just plugging in 4 for y. If I plug in 4 for y, then I get 16 here, so that's 2x squared equals 18, and so x squared equals 9, doing a little bit of stuff in my head there. Therefore, I'm going to have a point 34, but also a point negative 34. But also, when y is negative 4, I'm going to have 2 solutions. And once again, if you plug in negative 4 for y, you're going to get the exact same thing. 16 plus 2 is 18 divided by 2, x squared equals 9. So you again get plus or minus 3. Okay, so yeah, I think I'll stop. I'll stop talking because I'm just repeating myself. But yeah, the algebra is all correct, and the geometry supports the algebra, so everything's looking good. Okay, then when it comes to part B, this was the one that I believe I chose to do in all classes. I'm pretty sure I did part B in all classes, so I won't do it again. Part C, I don't know, I just don't feel like doing it right now, so I think I won't. Part D is quite difficult, and I don't know, it takes like 15 minutes or something, so I think what happened is in period 3 I didn't do it. In period 4 someone asked, and I was like, yeah, sure, we're being spontaneous here and stuff, and so I did it. And then we kind of ran out of time, and in period 6 I didn't. So, okay, so for periods 3 and 6, or anyone in period 4 who wants to see it again, I shall now do 4D. Alright, so this is quite a challenging problem, but it's challenging not, well, it's just overall challenging. The algebra is hard, the numbers are big, the graphs are difficult, but there's nothing, you know, mind-blowing about it, but it is just, you know, it's just a big old math problem. Okay, good. Let's begin. I've already sort of explained my position on this. We're going to do the algebra, but we're also going to make the graph so that we have a general gist of what this thing looks like. What does this thing look like? Well, it's going to be a hyperbola, the first one. And the second one is also going to be a hyperbola. Hold on, let me just take a big drink of coffee here. So, what kind of hyperbola? Well, if I divide both sides by negative 44, that gives me x squared over negative 44 minus, or plus then, 5y squared over 44 equals 1. That's not a very convenient form to have that hyperbola in. So let me try something better. Let me write it as y squared over 44 fifths minus x squared over 44. And again, I think the author of this problem picked the numbers to work out nicely algebraically, but that means that when it comes to producing a rough sketch, I have like these kind of disgusting numbers. What is 44 fifths roughly? Well, it's very, very close to 9, because 45 fifths would be 9 exactly. So this is like, once again, I guess I should just be able to do this. It's like 8.8. Is that just like true? Yeah, because it's 40 and 4 fifths. Keeping in mind that that's just 8.8, this is going to be a horizontal, a vertical hyperbola. What's the square root of 8.8? Well, it's very close to 3, right? So this is, I don't know, 3.9, something like that. So we should think of this as y over like 3.9, not 3.9, 2.9, tiny bit less than 3. So y over 2.9 squared minus, and what's the square root of 44? I don't know. More than 6, but less than 7. Not that much less than 7. I don't know, 6.7 or something. That's not necessarily accurate, but it's not terrible either. Okay, and so here, what I have just done, like I did before, is to get this first equation in standard form so that I can produce a graph. Alright, good. And then the other equation, xy equals negative 24, we learned via an earlier problem on this homework that is in fact a hyperbola. Okay, so that's exciting. Let's now make a graph. Alright, well, Okay, let's make this graph first because I know how to make this one sort of a little bit more accurately. What is x, y equals negative 24? Well, it's just like y equals negative 24 over x. So it's just like a y equals x curve, y equals 1 over x curve, but flipped upside down and stretched out by a factor of negative 24. So it's going to live in quadrants 2 and 4, and it's going to be, quite out here, right? There's going to be like, when I plug in 1, I get negative 24. When I plug in 2, I get like negative 12. When I plug in 3, I get negative 8. When I plug in 4, I get negative 6, etc. So I might not even try. I might just do this and kind of call it a day in terms of accuracy. Or I might just try to fix that up later. Can't decide. That seems good enough for now. What else? This one. What's up with this? It's a hyperbola, vertical, centered at the origin. Y is being stretched out by a factor of 3, sure. And x is being stretched out by a factor of 7, sure. So, and yeah. What kind of hyperbola is it? It is vertical, as we said. So, the vertices will be here at, 2.9 away. And yeah, that's it. So actually, this just really wasn't too hard. And already I can tell you what's going on. What I can tell you is that there are going to be two solutions. There's going to be one here, and there's going to be one here. So I should expect one in quadrant 2 and one in quadrant 4. And this is symmetric with respect to both the x and y axis, and this is also symmetric with respect to sort of the origin with respect to a 180-degree rotation. Therefore, I'm going to expect these two numbers to be kind of opposites of each other, 180-degree rotation away. Alright, now feeling very confident about the geometry of the situation, I can turn my knowledge of the conic sections kind of off, and I can just grind out the sort of algebraic solution here. And yeah, there are sort of two ways to do this. Both work, but one is better than the other. And I think the thing that works out better is to solve for x. So if I solve for x, x is negative 24 over y. And what I'm going to do is simply take x equals negative 24 over y and stick it in for x. The goal in solving any system of equations is just to, do something so that it's now reduced down to just a single equation and a single variable. So some kind of substitution method usually will work, and this is the one I'm choosing. Okay, so what does that mean? It means this entire equation becomes negative 24 over y, quantity squared, minus 5y squared equals negative 44. And now, indeed, this is just algebra 1. This is just a really, really hard algebra 1 problem. And you probably should just use technology to solve a problem like this, but this can be done by hand. I will do it right now in a kind of show-offy fashion. So this is good. It's a good problem to put on a functions test or something like that, and to give them 3 minutes to do it and see if they can handle it. What is 24 squared? Well, I know my perfect square is up to 25 or so I can tell you that that's 576. So that's 576 over y squared minus 5y squared equals negative 44. And this is one of these problems that you did in the first couple of weeks of Precalc A. It's not totally obvious, but if you sort of simplify by getting rid of fractions and multiplying through by y squared, then that's going to be effective because this is now a quartic, which has only like a quadratic and a quartic term. In other words, it's really like a quadratic in y squared. So what do we have? We have 5y to the fourth minus 44y squared minus 576 equals 0. And now this just reduces to a simple factoring problem. How do we factor this? Well, if I was really doing this just purely by hand, then I need to list all the factor pairs of 576. Yikes, this is what I did during fourth period. What are the factor pairs of 576? Well, we already said that 576 was 24 times 24, right? So this is like 8 times 3 and 8 times 3. In other words, what is 576 really? It's 6 2s and 2 3s. So now that I have, well, I kind of stopped halfway because I got bored, but this really is 2 to the 6th times 3 squared is the prime factorization of 576. And so it now becomes a kind of an algorithm to write every single possible factor pair of 576 if I really want to. So 1, 2, 3, 4, 6, 8 is certainly a factor, 9, 12, 16, 18, and I think then the last one is 24. So that's 24 times 24. That's if 18 is just 9 times 2, so I have 32 left over. 16 is, then that gives me 9 times 8 left over, so that's sorry, that gives me 4 times 9 left over. That gives me 36. If I take 12, then I took 1, 3, and 2 2s, so that gives me 16 and 3 left over, so that's 48. If I take 9, then that gives me 64 left over. In general, I think you guys are hopefully seeing how I'm doing this. If I take 8, then I have 8 times 9 is 72 left over. If I take only 6, then I have 32 times 3. And okay, I can just keep doing this if I really, really want to, but I kind of don't want to. So I'll leave those blank. If I need them, I'll go back for them. What was the point of all of this? I listed out every single factor pair of 576. And by the way, we know from the combinatorical unit back in December that, you know, I have sort of 7 choices about how many 2s to pick. 0, 1, 2, 3, 4, 5, or 6. And I have 3 choices about how many 3s to pick, 0, 1, or 2. So I should be expecting 21 possible factors of 576, and that's what I get, right? Because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns of 2 each, that's 20, and then that's 21. So I really did find all the factors. Now I am just using my tried and true quadratic factoring technique to look for differences of 44. So I need diagonal products whose differences are 44. And okay, I kind of did this already. So now I see it. In class I struggled a little bit, but this is 50 and 40 is 90 and 32. No, that's wrong again. 80 and 36. There we go. Cha-cha. So, yeah. 1 times 36 is 36. 5 times 16 is 80. And so indeed, I found the factorization. It's y squared 16 times 5y squared 36. And what is it? 5y squared, it's going to be plus 36 minus, plus 36y squared minus 80y squared gives me negative 44y squared, so I'm checking as I go. Alright, after much work, what have I learned? I've learned that y squared equals negative 36 fifths. No, I don't think so. Or y squared equals 16. And so indeed y is going to be plus or minus 4. And now, finishing off this problem, what if y is 4? What is x? Well, if y is 4, then x is negative 6. Boom, boom, boom. This looks exactly right. And if y is negative 4, then then what is x? Answer positive 6. And so, kind of exactly as I expected, the solution set for this system is this set of 2 ordered pairs, and kind of there it is. So there we go. Woo! All right, that was hard. Now, unfortunately, I did want to talk a little bit about the final section, which was the section on quadric surfaces. And okay, I wanted to go over this in class, and I did go over this in class on in periods 3 and 6, but in period 4 we ran out of time and did not go over it because we did live in class, the problem that I just did. So let's just do this now really fast. And what I mean by really fast is, like, pretty fast. So let's go. We have these surfaces, these so-called quadric surfaces. What are quadric surfaces? Well, this actually is not the most general analysis of them. There are some of them that we are not going to talk about in this class that you will actually study when you study multivariable calculus. But the simple ones, which we're going to be exposed to right now, are ones which can be formed by taking conic sections and rotating them in 3 dimensions about one of their axes. Okay, and so this is number 5 now. Let's just do this, and that will be the end of the video. 5a is a paraboloid formed by rotating the part of the graph of y equals x squared from x equals 0 to x equals 3 about the y-axis. So I have this parabola, y equals x squared. It looks like this. That's the point 3, 9, because they told me to use only the part of the graph from x equals 0 to x equals 3. And what happens if I take this shape and rotate it about the y-axis? Well, what I get is a paraboloid. And okay, what's it going to look like? You just have to use your imagination, art skills, technology, or whatever. It's not even a very good picture to see that. It looks kind of like that. So what we get is some kind of like bowl action. That's as good as I can draw. That's as good as I'm going to draw. So it's just this parabola, and you just boom, there it is. Great. 1 down, 4 to go. Part B. We have an ellipsoid. What is an ellipsoid? Well, actually, an ellipsoid more generally is a sort of 3D shape, which is kind of like a sphere, but which has been stretched by some factor sort of uniformly in the x, y, and possibly in z direction as well. So actually, you could have an ellipsoid whose kind of diameter, so to speak, in the x direction is like 3, and the diameter in the y direction is 4, and the diameter in the z direction is 5. That would be an ellipsoid, the most general kind of ellipsoids. But we are not going to look at those. We are going to look at only a particular kind of ellipsoid. These ellipsoids are called spheroids, and they're called spheroids because they can be formed by taking an ellipse and rotating it about one of the axes. And so, okay, let's just do the problem right now. What do we get? We get this. There's this ellipse. Boom, 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 boom. And the x-coordinate has been stretched out by a factor of 2. So it's just a normal ellipse. And I'm barely going to even draw anything. I'm just going to kind of talk about it and then nod or something. What can I say about this ellipse? Well, it's being rotated about the x-axis. So if it's being rotated about the x-axis, then I'm going to get like a whoosh, 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 whoosh kind of thing. And this one is going to look kind of like a mento, or a curling stone, or some people say cheese wheel, or a jelly donut. Okay. This has a name I kind of like already forget. It's like maybe oblate spheroid or something like that. But what's sort of key is that two of the dimensions of the spheroid, I didn't say this in class, are going to be the same, right? If you now think about this 3D shape, if you're picturing the same 3D shape I am, this kind of mento, right? In the this direction, it's going to have diameter 4. In the coming out of the board direction, it's also going to have diameter 4. And in this direction, it's going to have, it's going to have diameter 8, is what I meant to say. It's going to have diameter 8 in this direction. It's going to have diameter 8 in this direction as well. And it's going to have diameter 4 in this direction. So it's an ellipsoid, but it's specifically an ellipsoid which, well, I'll leave it at that. Okay, part C. Well, part C is just the same thing, but now let's rotate about the y-axis. So I'll just use the same figure because I'm kind of being lazy, is what I did in class also. What if I now rotate about the y-axis? Now what? Well, now I'm going to get this kind of like zoom, 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 zoom thing. Now this is kind of like going to be like a potato, or maybe like a football, like a rugby ball, or I believe that the football they use in Australia is actually one of these spheroids, prolate spheroids. I believe I have that right. And now you can see that if you do zhoo, 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 now it's going to have diameter 4 in this direction, diameter 4 in the coming out of the board direction, and diameter 8 in the this direction. Okay, great. I think this is a little bit important because, of course, we live in a three-dimensional world, so our study of the conic sections is a little bit limited if we only talk about 2 dimensions. In fact, when we really sort of meet the conic sections is in their kind of 3D variations. So, good. La 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 la. Last thing, 2 more, D and E. Let me just write them on the board right now. This is x squared minus y squared over 4 equals 1. And not all of it, only between x equals 1 and x equals 2. And we're going to rotate about the y-axis. Okay, and part E, I'll just get this up on the board now as well. This is also going to be a hyperboloid, but it's the hyperboloid x squared over 4 minus y squared equals 1. And only the part between x equals negative 5 and x equals 5. And now we are going to rotate about the x-axis. Okay, so let's talk about these 2 things, kind of what happens. Well, first let's just draw in the hyperbola, which is being rotated. What kind of hyperbola is this? It's going to be horizontal. The x-coordinate's not being stretched out, but the y-coordinate is being stretched out by a factor of 2. So I make my happy box, and the actual hyperbola is going to look like this, but only the part from x equals 1 to x equals 2. And so I'm imagining something that looks kind of like that. Okay, so this is kind of like a truncated, yeah, that's supposed to be 2. This is like a truncated hyperbola, or one branch, a truncated branch of a hyperbola. Okay, great. So what? Well, now rotate this about the y-axis. And if I rotate this about the y-axis, what shape is being formed?
Just a second.
Answer. I'm going to be done in like 30 seconds.
Better be.
Okay. The answer is, it's going to be a this. This has a name. This is called a hyperboloid of 1 sheet. And there are lots of things which are shaped like this. You can make a basket that's in this shape by starting with a circle and adding straight sticks at a certain fixed angle. And for that exact same reason, it's very structurally stable. you will find that some nuclear power plants are shaped like this. I think it's kind of got Chinese yo-yos are kind of shaped like this as well. So, okay. Great. Last problem for real. This one, what does this look like? Well, now we have a hyperbola which has been stretched out by 2 in the x direction, 1 in the y direction, so happy box. And now I'm supposed to be going only from -5 to 5. So that's maybe -5, say, over there. So the hyperbola looks like this, and that's maybe 5. Alright, so this is a truncated hyperbola, 2 branches of that hyperbola. Then what am I doing? I am rotating it about the x-axis. Well, if I'm rotating about the x-axis, now I'm going to get this 3D shape, and it kind of looks like 2 sort of like cups. And this is called a hyperboloid of 2 sheets. Well, this is sort of a disconnected surface. So this is a surface it's in two sort of separate pieces from each other. Okay, so that's just a very, very kind of shallow introduction to quadric surfaces, surfaces of rotation. That's all I got. Goodbye.